We're in section 9.3 of Rosen, Discrete Mathematics and its Applications. The topic is representing relations. We've looked at a couple of ways of realizing relations, the roster method, arrows between elements of sets. Here we're going to look at two more, matrices to represent relations, and then digraphs or directed graphs. This video will cover the matrix representation. So if we have a relation, we can represent it with a 0, 1 matrix. And the way we do that is if we have a relation from A to B, and A has m elements and B has n elements, then we'll use a matrix with m rows and n columns to represent the relation. And the ordering isn't important until you establish the matrix, and you have to keep in mind the ordering of the elements. And if we're going to use a matrix to represent a relation, what we do is whenever an ordered pair is in the relation, we put a 1 in the corresponding entry in the matrix. So aibj in the relation means we get a 1 at the position ij in the M matrix. And if it is aibj is not in the relation, then a 0 is inserted. That's what this last line says. All right, so for example, we have two sets. The first set is A, second set is B. R is the relation from A to B, where A is greater than B. So what will the relation look like? Well, it's going to have three elements, all of the ordered pairs in the Cartesian product of A and B, where the first coordinate is greater than the second coordinate. And so what will the matrix look like? That's going to be a 3 by 2 matrix, 3 elements and 2 elements. And we can see that 1, 1 would not be in the relation because 1 is not greater than 1. But 2, 1 is in the relation. This corresponds to the entries this way, 1 and 2. 3 is greater than 1, and 3 is greater than 2. All right, here's a matrix representation on for the relation from A to B. And what are the ordered pairs in it? Well, this will represent the A portion and the B portion. And we can see that A1, B1 is not in the relation, but A1, B2 is in the relation. And then A2, B1 is in the relation, and so forth. And there's 7 entries in our matrix, so there will be 7 ordered pairs in our relation. And just for circle one more, A3 and B5 is in the relation, and we see it right there. When we have a relation on a set, that means it goes from and to the same set. In that case, the matrix will be a square matrix. And as with earlier discussion of matrices on set or relations on sets, we can examine certain properties. One is the reflexive property. If R is reflexive, then all the elements of the matrix representation on the diagonal will be 1. And then 2 more properties. For the symmetric property, we have to check the positions with the indices switched. So if Mij is 1, then we look for the Mji element, and if it's also 1, or they have to be equal, so if Mij is 0, then Mji has to be 0. For every off-diagonal element, they have to be equal. Then you will have a symmetric relation. For the anti-symmetric relation, property, we look at off diagonals with indices switched, and if one is a 1, the other one has to be a 0. They can both be 0, but again, if only one of the two corresponding entries with indices switched can be a 1 to be antisymmetric. All right, so let's look at a matrix relation for a relation on a set. So it's a square matrix, 3 by 3. The question is it reflexive, symmetric, or antisymmetric? Well, we have ones along the diagonal, so it is reflexive. Every place where we have an off-diagonal entry, the corresponding entry with the elements switched is the same, so we are symmetric. And then we have M32 and M23 are both 1. That can't be the case for an antisymmetric relation, so this relation is not symmetric. And there's the solution, which will be in your slides. And that is matrix representations of relations.